Last lesson we learned about these things called functions, and in this lesson we take it an extra step and we talk about linear functions. Now, a linear equation with two variables, x and y, that's our standard, is an equation that can be written in a special form, and the form is y equals mx plus b. Now, in this form, m and b are constants. And remember, we talked about what constants are in an earlier lesson. Constants just stand for numbers. So we would put numbers in the spot for m and b, and we would leave x and y. And the reason that we leave x and y is because these are usually drawn on the coordinate grid. So we need an x value and a y value in order to graph it. Another fact is that the graph of a linear equation is a line, just like the word linear has the word line in it, so it makes a line. So a linear function is a function whose graph is a non-vertical line. And a vertical line would not pass the vertical line test because the dotted vertical line will go through the entire graph. And so that's just the exception. But typically, lines are functions, and we call them linear functions. A linear function has a constant rate of change, and we're going to talk about rate of change. You also kind of know rate of change. You talked about it last year in 7th grade with the phrase constant of proportionality. So that's kind of like the rate of change. We're going to extend it a little this unit. And a nonlinear function does not have a constant rate of change. So therefore, it doesn't create a line. So very simply, in example 1, we just have to say whether the graph is linear or nonlinear. Now, the way that you do that in a picture is you just say, is this a line or is this not a line? Now, obviously, I hope you would look at letter A and say, well, obviously that is not a line, so it is nonlinear. And all we say is, not a line. And letter B is linear. And the reason is, it is a line. It does not get easier than that when you have a graph. It gets a little trickier when you have a table because you have to look for what we talked about before, which is the rate of change. So, let's look at the x values. So the x values here are going up by 3, 3, 6, 9, 12. So that's a constant pattern. But do the y values also have a constant pattern? So 36 to 30 goes down 6. Does that minus 6 pattern continue? And yes, it does, right? So everything is being subtracted 6. So since that pattern continues, that's what makes it linear. Sorry, that keeps zooming. So then we say linear, and the reason is it has a constant rate of change. All right, now let's look at letter B. The x values are going up by 2, so that has a constant rate of change. But do the y values. Now the y values go from plus 7, then it goes plus 11. So obviously it's not a constant rate of change, right? And then it goes plus 15. So it might be a cool graph, but it's not linear. It's not going to create a line. So you just reverse the answer from letter A, nonlinear, because it does not have a constant rate of change. The next thing that we're going to look at is linear functions when they're written as equations. Now remember, a linear function is in the form y equals mx plus b, where m and b are numbers and y and x are just y and x. It has to look like that, or some sort of like movement of that, right? Like you can move things around. So I hope that you recognize that fourth one. If you just distribute, you'll get 6x minus 6, which almost identically looks like y equals mx plus b. So that one's linear. All right, now there is one other equation that is linear. Can you tell which one it is? It is the very first one. You can rewrite that as y equals 0x plus 3.8. That looks like y equals mx plus b, right? Because 0x means you don't write any x's, and so therefore that's why the equation doesn't have any x's. Now, this second one right here, y equals the square root of x, is not linear because here there's no square root symbol. This one has this fraction with an x in the denominator, and if you look at the format, the formula, the x is not in a denominator anywhere. And this one has an exponent, which is also not in the format. So linear functions cannot have a square root, they cannot have x's in the denominator, and they also can't have exponents. All right, now let's talk about solutions of a linear equation. When you're talking about solutions of a regular equation, you're just talking about the values of x. But since these equations have x and y, we're looking for an ordered pair. The graph of a linear equation is the set of points on a coordinate plane that represent all solutions of the equation. So kind of like an inequality, but not necessarily because it doesn't have that shading on the number line. Sometimes the points are connected, and sometimes they're distinct, meaning they're individual values. So down here we've got an example. Discrete would be an example where they're distinct, right? They're just individual value points. Like if I say, what are the integers from 1 to 5? Now remember, integers don't have any decimals on them, so we're just looking at the numbers 1, 2, 3, 4, and 5. A continuous or a connected domain would be all of the values between a range. So if I say all numbers from 1 to 5, then I'm talking about decimals and fractions and irrational numbers, repeating decimals, right? Like all those numbers. And so we would do the shading. So let's talk about some discrete information. A linear function, y equals 15.95x, represents the cost in dollars of x tickets for a museum. Each customer can buy a maximum of 4 tickets. So let's find the domain of the function. So if you can buy a maximum of 4 tickets, that means that you can obviously buy 0 tickets, right? Like you don't have to buy any tickets all the way through 4, right? But you can't buy like 2.7 tickets. So the domain is only the numbers 0, 1, 2, 3, or 4. Then they ask, is it discrete or continuous? Remember, discrete means that you can only use specific values, and continuous means that there's a nice range. And I just mentioned before that you can't buy a fractional ticket, so that means it is discrete. And then the last thing that we have to do for this question is to graph it. So as I graph, well, that was weird. As I graph, I'm going to only do the values 0, 1, 2, 3, and 4. So I'm going to have myself land in the first quadrant only. So there's quadrant 1. I'm going to label X and Y. And X is tickets. And what's Y? Dollars. So I can buy 0, 1, 2, 3, or 4. And I'm just going to round, that's 16 and 16. So it's 16, 32, 48, 64, and whatever. Hopefully I don't need to keep going. Anyway, all right, so if I buy 0 tickets, then it costs me $0. If I buy 1 ticket, it costs me $15.95, which is basically $16. So, like, give me a break. We'll just go right underneath. All right. And then if I buy 2 tickets, it's $31.90, which is almost 32. If I buy 3 tickets, it's $47.85, which is almost 48. So let's get really close to 48. And then if I buy 4 tickets, it's $63.80, which is basically $64. So We're going to go pretty close. So whoops, wrong spot. There we go. All right, now since it says that you can't buy more than 4 tickets, that's as far as I can go, and I'm not going to connect them because I can't buy a fractional ticket. Here's an example of continuous data. A cereal bar contains 130 calories. The number of calories consumed is a function of the number of bars eaten. So does it represent a linear function? And it does, because every time you eat a bar, your calories go up by 130, right? So it's not like you eat 1 bar, it's 130 calories. You eat 2 bars, it's 275 calories. You eat 3 bars, it's 4,000 calories, right? So there's a constant relationship between the number of bars and the number of calories. Now what we have to do in letter B is find the domain, so the first thing that we want to think about is what kind of numbers make sense for the number of bars that you eat. So can you eat half a bar? Sure. Could you eat 1/4 of a bar? Sure. Could you eat 100 bars? I don't know, maybe you might get sick. But you can. So if B represents the letter they want us to use, the domain is B is greater than or equal to 0. Because you can't eat negative bars, you can eat no bars, or anything greater than 0. Next question is it discrete or continuous? So since I just mentioned you can eat a fraction of a bar, then it is continuous, because you can eat a half a bar, you can eat a third of a bar, you can eat, 2.7 of a bar. You can keep taking little baby bites and keep getting tiny fractions of a bar. So I said it's continuous because you can eat any value of a bar. Now we have to graph using the domain. So now we know that the domain is B is greater than 0. Well, that's crazy. It happened again. So we're all gonna stay in that first quadrant. And I'm gonna label. So this stands for bars, and this stands for calories. And I'm gonna label my axes. I can have 1, 2, 3, 4. And let's go 130, 260. I don't need to keep numbering, but that's the pattern. Here's 0 down in the corner. So I can eat 0 bars, and I can also eat 1 bar. I could eat 2 bars. So you kind of see the pattern in the picture. It would look like this. It would just kind of go straight through those dots, continuous, because I can eat any portion of a cereal bar. Last section is for you, and I'm going to ask what you put when we see each other in class. I want you to come up with a real-life problem that would fit the data below. And the domain of this is discrete, and the domain of this is continuous. So pay attention to your labels. The graphs are very similar, but one is discrete and one is continuous. So write me some stories, and if you have any questions, write them down and ask me when you come to class.